Have you ever wondered how GPS technology works? How does this global positioning system pinpoint your exact location on Earth? Welcome to the fascinating world of GPS, or Global Positioning System. It's a technology so ingrained in our daily lives, it's easy to take for granted. From guiding us to the nearest coffee shop to tracking our morning run, GPS is everywhere. But what is it exactly? GPS, in essence, is all about time and location. It's a system that can tell you where you are, anywhere on the planet, at any time of day. Sounds like magic, right? But it's not wizardry, it's science. At the heart of GPS are satellites, those celestial machines that orbit our planet. There are currently around 30 of them circling the Earth, each broadcasting a unique signal. This signal is picked up by GPS receivers, like the one in your smartphone, and is used to calculate your precise location. But how does this work? Well, that's where things get a bit complicated. You see, each GPS satellite carries an atomic clock, the most accurate timepiece known to man. The signal each satellite sends out includes the precise time when it was transmitted. Your GPS receiver picks up these signals, noting the exact moment they arrive. By comparing the time the signal was transmitted with the time it was received, the receiver can calculate how far away the satellite is. Now imagine doing this with signals from 4 different satellites simultaneously. With the distances to these 4 satellites known, your receiver can pinpoint your exact location. This process is known as trilateration, and it involves some complex algorithms and a whole lot of math. And there you have it, the magic of GPS, stripped back to its core principles. It's a symphony of science, a dance of distances, and a testament to human ingenuity. By the end of this video, you'll understand the basics behind this incredible technology. First, let's talk about the eyes in the sky, the satellites. These celestial bodies are the backbone of the Global Positioning System, or GPS. Imagine a network of 24 satellites orbiting around the Earth. They're not randomly scattered, but rather meticulously arranged into 6 orbital planes to ensure each and every point on Earth is covered. It's like a celestial ballet, with each satellite dancing to the rhythm of precise mathematical choreography. Now, you might be wondering, how high are these satellites? Picture this. Commercial airplanes fly at an altitude of about 7 miles. These satellites, on the other hand, orbit at a staggering altitude of over 12,000 miles. That's nearly 2,000 times higher than the height at which your average airplane cruise. The role of these satellites is simple yet crucial. Each of these satellites is like a lighthouse in the sky, continuously transmitting 2 key pieces of information: its exact location and the precise time the message was sent. This is done through a digital data message that includes a timestamp, the satellite's location, and some other less crucial data. Interestingly, every satellite contains an atomic clock, one of the most accurate timekeeping devices known to humanity. Thanks to these atomic clocks, the time data transmitted by these satellites is incredibly precise, to the billionth of a second, in fact. The satellite's location data, on the other hand, is not as dynamic as you might think. Given that each satellite follows a specific path, their locations at any given point in time are predictable. This information is pre-programmed into the GPS devices we use, which helps in calculating distances. So, these satellites are continuously broadcasting their own position and time. But how does this data help us find our location? That, my friends, is where the magic of GPS technology truly begins. But we'll delve into that in the next scene. Stay tuned. Now, let's turn to the unsung hero of GPS, the receiver. The receiver, a small yet powerful device, is nestled in everyday gadgets like your smartphone, car's navigation system, or a hiker's handheld GPS unit. It plays an indispensable role in making the magic of GPS possible. But what exactly does it do? To begin with, the receiver is the device that picks up the faint signals transmitted from the satellites orbiting high above. Picture this. You're at a crowded party, trying to listen to a friend across the room. Amidst the noise and chatter, your ears pick up their voice. That's somewhat akin to how the receiver functions, diligently tuning into the signals from multiple satellites amidst a sea of electromagnetic noise. But picking up the signal is just the first step. The real genius of the receiver lies in its ability to calculate the time it took for the signal to arrive. Each signal carries a timestamp, marking the exact moment it left the satellite. By comparing this with the time of arrival, the receiver works out the signal's journey time. Remember, light and therefore radio signals travel at a staggering speed, around 186,282 miles per second. So even a tiny delay in arrival time translates to a large distance. The receiver uses this information to determine the distance from each satellite. Now, you might wonder, how does the receiver know the precise time? It doesn't have an atomic clock like the satellites, after all. Well, that's another marvel of the receiver's design. It uses the signals from at least 4 satellites. This allows it to solve for the exact time, along with its location in 3 dimensions: latitude, longitude, and altitude. So we've seen how the receiver picks up signals, calculates their travel time, and thereby determines its distance from each satellite. It's a process that happens in the blink of an eye, yet it's crucial for the functioning of the GPS. So the receiver knows how far it is from several satellites. But how does this translate into a location on Earth? This is where the magic happens, a process called trilateration. Let's take a moment to break down this seemingly complex term. Trilateration. It sounds technical, doesn't it? Well, it's not as complicated as you might think. In fact, it's a concept you've likely used without even knowing it. Imagine you're playing a game of Marco Polo in a swimming pool. You're blindfolded, but you have to pinpoint the exact location of your friend who's calling out, "Polo." How do you do it? You listen for the sound of their voice, and you move towards it. But it's not just the direction that's important. The volume of the voice also matters. The louder the sound, the closer you are. That's a basic example of trilateration. Now let's apply this concept to GPS technology. In the world of GPS, satellites play the role of your friend shouting "Polo," and the GPS receiver acts as your ears, listening out for the signals. To pinpoint your location, the receiver needs to hear from at least 3 satellites. This is where the tri in trilateration comes from, indicating 3. Here's how it works. Each satellite sends out a signal that includes the exact time the message was transmitted. The GPS receiver picks up these signals, and by measuring the time it takes for each signal to reach the receiver, it can calculate the distance between it and each of the satellites. If the receiver knows it's a certain distance from satellite A, it could be anywhere on a large sphere centered around that satellite. Add in the distance from satellite B, and our possibilities narrow down to a circle where these 2 spheres intersect. Add in satellite C, and we get 2 possible points where all 3 spheres intersect. One of these points is usually impractical, like in outer space, leaving us with 1 plausible location. And just like that, through the power of trilateration, your location is revealed. So, now that we've broken down the workings of GPS, let's quickly recap. In essence, GPS, or Global Positioning System, operates through a network of satellites orbiting Earth. Each satellite is equipped with an atomic clock and transmits its precise location along with the exact time. This information travels at the speed of light to reach GPS receivers here on Earth. The role of the receiver, whether it's in your car, your smartphone, or even your smartwatch, is crucial. These devices capture the signals sent by the satellites. They then calculate the distance to each satellite based on the time it took for the signals to arrive. Remember, the signals are traveling at the speed of light, so even a millisecond difference in arrival times can equate to a substantial difference in distance. With data from at least 3 satellites, the receiver utilizes a process known as trilateration to determine your exact location. Essentially, each satellite provides a sphere of possible locations, and the point where these spheres intersect is your current position. The more satellites the receiver can connect with, the more accurate this location data becomes. But GPS isn't just about pinpointing your location on a map. Its real-world applications are far-reaching and integral to our daily lives. The most obvious application is navigation. GPS helps us find our way in unfamiliar cities, ensures we never get lost in the wilderness, and even guides ships across vast oceans. Beyond navigation, GPS plays a crucial role in timekeeping. Because each GPS satellite carries an atomic clock, the system can provide incredibly accurate time data. This is crucial for synchronizing telecommunications networks, managing power grids, and even executing high-speed financial transactions. Emergency services also rely heavily on GPS. It helps locate distressed individuals in search and rescue operations and plays a pivotal role in disaster management. And there you have it, the power of GPS technology, a system that connects you to the world and the world to you in the palm of your hand.